right? And then we had one where we had two groups side by side, right, with a charge and either a like a positive and negative side by side, or a lone pair and a plus charge, or something like that. Right. So in this case, I'm gonna do this. All right. So what group would this structure fall into? Out of these four choices, because that's one of the first things that helps us to know what we ought to do if we figure out what pattern is going to fall into.
What number are we doing again?
Right here. We're doing this example right here.
Okay.
And the question is, what pattern does it fall into? Is it a allylic cation, a allylic anion, allylic radical, or is it two atom unit? You can see here, right, you have a carbon with a plus charge right here, and it's next door to a nitrogen, in this case, with a lone pair. So this is the two atom unit where the donor and the acceptor, I'm just going to abbreviate it because by the time I write out donor, class will be over with. Donor and the acceptor right next door to one another. Right, and if we look at the resonance form, what does it look like happening? Going from here to here. What does it look like happening? Oh no, speak at once now. I know it's Friday. We down by 15% in attendance.
Dr. Russell, are you sharing a different screen? Because my screen is still stuck on Blackboard.
And my screen is sideways.
What about now?
It's better.
All right. So we're looking at this example right here. And the question is, first question was what pattern it fell into. The second question was, how do you move the electrons to take it from here to its resonance form?
Was it a two atom?
Yeah, it's a two atom unit. That's right. So look at where's the donor and where's the acceptor? That's the question. That's another question. So once you figure out the pattern, then you find the donor and the acceptor.
Isn't the donor the lone pairs?
Yes, the lone pair on nitrogen, good. And then that will make the carbocation adjacent to it the acceptor. Is that right? You always want your donor and your acceptor to be adjacent. If they're not, then they can't talk to each other. So what would you do?
I think it's only 20. Oh, shoot.
What would you do here to go from here to here? What would you do? What arrows would you put in to do that?
The arrow from the lone pair?
Good. You always start at your source of electrons, and then you're going to put it here. Right? Do you see that? I stop the arrow where I want the electrons to go. And so I want those electrons to become a pi bond between this carbon right here, right, and nitrogen. So I put the arrow between them. I didn't put it on carbon. What would that mean if I drew my arrow and stopped it on carbon? Right, wherever the arrow stops, that's where my electrons are. So if I draw it from here, let's say this is nitrogen right here, and this is carbon, right? If I draw the arrow to carbon like that, what that means is that I'll be putting a lone pair on carbon. Now I can't do that, right? So that's why I put it between the atoms to indicate that I'm putting a pi bond right there. All right? questions about that? So that falls into that category of a 2-atom unit. Let's look at the next one. Can somebody tell me why the formal charge here is positive before we do the next one?
Is it a-
Right, is what? Valence minus what? Actual. That's how I calculate the formal charge. Is that right?
Yeah.
What's the valence for nitrogen?
Is it
5.
5?
5. How many electrons does it have around it in this example?
No.
It's 1 from each bond.
4.
4. So 5 minus 4 would be plus 1. All right, let's do the next one. Right here. Let's see. All right. So in the next example, can I go straight from here to here?
No.
No. So what that means is that I'm going to have multiple resonance forms in between where I started and where that finishes. Are you following that? Why don't you take about a minute, 2 minutes, and try to draw. I'm gonna put the arrows in for the first one, and I want to see if you can draw that form. Matter of fact, I'll put the arrows in. I'll be responsible for that, and then y'all tell me what the next resonance form is gonna look like. So I'm gonna put that right there. Man, I can't do this on my iPad. And I'll put these right here. All right, so what would that look like? Still gonna be a ring. It won't look like that though. Is that right? Still gonna be a ring, yes. And you
Yeah.
have a double bond between the ring and this carbon on the outside. That CH2 is out there. Where's that pair of electrons going to be?
It's gonna be
The left.
It'll be on this carbon right here, won't it?
Mm-hmm.
It's going to have a negative charge. What pattern does that fall into? Can I highlight that?
in
Right, here's my pattern right here. So what out of the 4 patterns that we looked at, allylic anion, allylic cation, allylic radical, and a 2-atom unit, which one would that fall into?
Allylic anion.
Yeah, you know it's an anion because it's negative, right?
Mm-hmm.
And then the double bond being adjacent to the negative charge, it's an allylic anion. I promise you, if you can identify those patterns, the rest of it becomes cake because the flow of electrons never changes for each pattern, no matter where you find it. When you push the electrons, it's the same method for each pattern. Right? Do you see the pattern again here?
Yes.
You got a anion and adjacent to a double bond. So I'm going to push those electrons again here. Right there. And I'm going to take these and I'm going to push them right here. Can you see how it's the same 2 arrows that we did up top? It's just in a different location.
Mm-hmm.
It's the same. It never changes. That's why I want you to learn the patterns so that the electron part will be just very simple. You just sticking the electrons in. All right. So what's that new structure going to look like?
You're gonna push your electrons to the next carbon, and then you're gonna remove one of the bonds within the ring.
So is this what you have for that?
Yes.
Hmm? And then from here, this is how I can get to here. Are you following that? Right? How would I do that? What would you do to go from here to here?
The same process.
Same process, because you can see that same pattern right here, can't you?
Yes.
Same process. Boom, you put that there, and take this pair of electrons and stick them right out here on this end carbon. Right, and that's going to take you to that top structure. So you can see you can't go directly to it, but you can get to it through doing multiple resonance forms. Any questions about that so far? All right. I'll leave that right there, just in case somebody's still writing it. What about the next structure right here?
Which one?
Right here.
Oh.
How you gonna go from there to here, to the other side? What would you do? What happened? And what pattern does that fall into?
I want to say
2 atom?
2-unit atom or a radical.
Well, look at the atoms that are participating, right? So you got oxygen right here, you got carbon, and you got nitrogen. You see that? It's the same over here. So it can't be 2 atom unit. It's got to be one of the threes. It's more similar to a allylic anion, right? Because you got a lone pair of electrons out here that you can share with this carbon. So it's just not charged, but it's more similar to one of the allylic systems.
So it's a radical?
It's not a radical, because a radical only has
Oh.
one electron.
Oh yeah, that's right.
Yeah. So it's closer to an anion than it is a radical. It's just not. It just doesn't have a charge in that first structure.
Mm.
That falls into that category. So how would you go from here, right here, to here? What would you do?
Donate the lone pair.
Donate the lone pair. Good. Why'd you want to do that? Who was that?
Bethany.
Why would you do that, Bethany?
Because
You're right. I'm not trying to say you're wrong. I'm just asking why'd you think of that?
Because like you were saying yesterday, like you have to, well, from what I see in the next one, like the other structure, it has like the plus charge on it. So like when you donate the lone pair, it donates those electrons and gives it to the acceptor.
Mm-hmm. So this is my donor, right? And that makes the pi bond the acceptor. Is that right?
Uh-huh.
Right. Also, in the other structure, you got a pi bond right here.
Mm-hmm.
Right. So that means that those electrons had to come from somewhere. And if you look at the nitrogen, the lone pair is no longer there. So it had to come from there. All right. Is that all we have to do?
No, don't you move that bond?
You got to break that pi bond, don't you? Otherwise, this carbon right here is going to be all screwed up. It's going to have too many bonds to it. So I need to take that pi bond and give it to oxygen. Is that right?
Yeah.
You see how it's the same 2 arrows, just like it would be for anion. It's the same idea. It's just applied to a different type of structure.
So what pattern was this again?
It was related to the anion, the allylic anion. You know how we had the allylic anion that looks like this? Like that?
Yeah.
Yeah, so it's it's similar to that.
Okay. Thank you.
All right. All right. I wish I could turn y'all loose for a second on these bottoms. I'm gonna try something on the bottoms. Let me erase this stuff over here too, because it's just gonna be in the way. This crap. All right. So let's go down here to the bottom, the next set of examples, and it asks you to follow the arrows and draw a second resonance structure. So let's look at the first example right here. What do you think happens there? You can see what the arrow is doing, right? What's the arrow telling us in that example?
Get rid of the bond. Get rid of.
Yeah, I'm breaking the one of those pi bonds in that triple bond. Is that right?
Yeah.
And I'm giving that pair of electrons to nitrogen. Yes. So this is, I'm gonna just abbreviate that CH. Let me just draw it as a line. So this nitrogen now has a double bond to it. It's got a pair of electrons, no charge, right? And then the other nitrogen here, what's the charge on it? Because the formal charge is just very, it's plus, it's positive, right? +1, good. Who was that?
Annalise.
All right, nice work. It's positive. Why did it become positive? How do I make it atom become positive? What do I need to do to it?
Take away electrons.
Take electrons away from it, and that's exactly what that arrow indicated. All right. Let's look at the next example. What's happening there? What is this arrow telling me right here?
It's adding the bond.
So it went between the atoms. That means that I'm taking this pair of electrons and I'm putting them here to make a pi bond. Is that right?
Yeah.
What is this arrow telling me? Look where it stops. It's stopping in between this carbon right here. Sorry. This carbon, right, and this carbon. So what is that telling me? Is it putting a pi bond between those two carbons? It is, isn't it?
Yes.
So this is the resonance form, what the resonance form would look like here. All right. Let's do the last one. Because that one has some, uh-oh. All right. Oh, I see a question in the chat. Hold on. Yes, yes, I'm recording it. All right, let's go to here. What pattern is this? Does this fall into? Is it one of the allylic patterns?
Is it the allylic cation?
It is. You got a plus charge next door to a double bond. And look at the arrow. It's the same arrow to do resonance for that type of system, right? This pi bond is going to shift over to here. And then I'm going to get come on, Russell. I'm getting this, right? And this is coming here like that with a plus charge here. And then the methyl group is out here. I'm not going to write out the CH3. And then that. Can I do that? Can I do resonance again?
Yes.
Because you see that pattern again, don't you? Right here.
Mm-hmm.
All right, so if I do this, not that, that's a half arrow. Well, it looks like a half arrow. Right, I'm going to get another structure. Here, double bond here, the methyl group is still out here. And then the plus charge is going to be down here. Yes or no?
I have a question.
Come on.
How do you know where you put the plus charge? Like, do you push it back like 2 spaces or what?
It's not about the spaces. It's about the carbon. So right here, let me just, so this right here is a carbon. Is that, you agree with that?
Yeah.
And it's got a hydrogen on it, right? It's got 4 bonds to it. If I move that pi bond and break that bond to that carbon, now it's left with only 3 bonds. So that's how I know where to put the charge.
Okay.
Right, the same thing here. Now, here we started out with a cation right here. Right, we started out with a plus charge. How do I know that carbon is positive? Well, it's got 3 bonds to it, and valence is 4, and the number of electrons around it is 3. So 4 minus 3 would be plus 1. And then if I break this pi bond here, what I'm doing is taking electrons away from that carbon. So that's how I know that carbon is going to become positive in the resonance form, which you can see right here. Did that answer it?
Yeah.
Okay. All right, any other questions about that? All right, so we're gonna, I'm gonna pause right here on this. I wanna go back to the first handout that we were working on from module 1, so I can find it. All right, let me see if I can share this iPad. Hopefully it's not all screwed up. All right, I want to ask you some questions off of here. Because I think that last question on there, you can do the first 2 questions we'll come back to, because it's going to take a little bit more instruction. It's dealing with isomers and things like that. So we'll talk about that when we get to on Monday, when we talk about the functional groups. I want to look at this question right here because we didn't talk about it. We'll close out with this. So in this atom, in this molecule, it asks what's the most electronegative atom, right? Which one is it? It can't be any of the carbons, right? So it's going to be between nitrogen, oxygen, and bromine. So you need to know your periodic table, right? It's carbon, wrong pen, carbon, nitrogen, oxygen, and then group 7 would be fluorine, chlorine, and bromine. What's the trend for electronegativity?
Doesn't it increase as you continue going to the right?
From left to right, and then from bottom to top. That's the trend. So of those three, which one is more electronegative?
Bromine.
Oxygen.
Oxygen. Because so bromine is, even though it's further to the right, it's further down too.
Okay.
So oxygen is the most electronegative atom here. Does that make sense? For who said bromine? I ain't trying to call you out. I just want to make sure that.
Kristen.
So, yeah, so the bromine is further down the periodic table than oxygen, even though it's further to the right. Right. Oxygen is actually the second most electronegative atom on the periodic table, other than fluorine. Fluorine is your most electronegative atom. All right. Are we okay with that?
Yeah.
All right. Let's go to the next question. It says, which of the following statements correctly describes the typical bonding of carbon, nitrogen, and oxygen? Right. What do you know about carbon?
It has to have 4 bonds.
Gotta have 4 bonds. So any answer that doesn't have carbon with 4 bonds is out. So we can rule out B
and D.
And D, right? So now we say A says it has 4 bonds, oxygen has 2, and nitrogen has 5. How many bonds does nitrogen have normally?
3.
3, right? So that's anything with nitrogen not having 3 bonds is out, right? So we can rule out A. Is that right? And then we can rule out, well, we can rule out A. So it's going to be between E and F, yes?
Mm-hmm.
Yes.
I'm sorry, C and E, because F is none of the above, my bad. So which one is it?
E.
It's E, right? Carbon makes 4 covalent bonds. Oxygen can make 2 covalent bonds and have 2 lone pairs left. And then nitrogen can have 3 covalent bonds with 1 lone pair. Anything else, and it's going to have some type of charge, right? If oxygen has 3 bonds, it's going to have a plus charge. If it's got 1 bond, it's going to have a negative charge. I think we went over that one day last week when we were talking about formal charge. All right, so let's go to number 3. It says of the molecules listed, which does not have a dipole moment? Does not have a dipole moment. How do we know if something's gonna have a dipole moment? What's the idea behind that?
If it's polar.
So what causes the polarity though? That you're right. What causes?
The electronegativity.
Yeah, the difference in electronegativity between 2 atoms in the bond. Is that right? So let's take HCl for instance. This is actually a covalent compound. Which one of those is more electronegative?
Cl.
Right, so the dipole is going to be going that way. Is that right?
Yes.
And what about this in Br, Br, Br? And this has a lone pair. Oh, that lone pair looks sloppy. Right? So of those 2, which one is more electronegative, nitrogen or bromine?
Nitrogen.
All right, and then the lone pair is in the orbital. So that lone pair is in an orbital going away. Let me erase the top one. In an orbital going away from nitrogen. Anytime you have a lone pair on an atom, that's an automatic dipole in the direction of that lone pair, right? And it's not symmetrical. So in all the other bromine and nitrogen bonds are going, bromine bonds are going that way. So you're going to have an overall dipole for that molecule. Remember, we talked about the dipole being a vector. And if you sum the vectors up, you're going to get an overall. It'll be the same thing for BF3. Right, but the dipoles are going here towards fluorine. All right, so you're going to have an overall dipole for that. What's the Lewis form for CO2? Keep in mind, this does not have a charge, right? So what's the Lewis form for it if it's neutral? And carbon and everything has a full octet.
Isn't it linear?
It's linear, that's right. It looks like this. So C, double bond O, double bond O. So when you're talking about dipoles, because I know this was in that video, what is the, what's the word I'm looking for? What's the consequence of a molecule being symmetrical?
Nonpolar.
It's nonpolar, right? This is going to have these dipoles are actually going to end up canceling each other out because you'll have a dipole going that way and a dipole going that way. So that symmetry is going to cancel out the dipoles, right? Yeah, it's true. So CO2 is going to be the one without a dipole. All right. So what about number 4? When it says list in order of increasing electronegativity. Increasing means from least to greatest.
So wouldn't it be D?
It's D. Because what's the greatest? What's the highest electronegativity?
F.
It should be fluorine. And that has to be, it can't be C, right? Because if it's C, that means fluorine is the weakest, going from fluorine to rubidium to oxygen. So it's got to be, the answer is D. It's not listed. It should be RB and then O and then F. All right. What about number 5? A polar covalent bond. Do the atoms have greatly or slightly different electronegativity? I don't think I mentioned that, but let me give that to you. So for a non-polar covalent bond, it's in the difference in electronegativity is anywhere from 0 to 0.39. And then for polar covalent bond, it's going to be from 0.4 up to 1.5. All right, so it's a pretty big difference between the electronegativity of the 2 atoms in the bond, right? So it can't be here, right? What happens when the atoms have equal electronegativity? Wouldn't that be non-polar? Wouldn't that be non-polar? Yeah. So what if they have slightly different electronegativities? That's also going to fall into the range of a non-polar covalent bond. So there has to be a big difference between the electronegativity. So from 0.4 up to 1.5. So you just calculate that by subtracting out, taking the difference in the 2. And then D is not covalent. D is ionic. So a covalent bond equals shared electrons, and then the ionic is electrostatic attraction. That just means that something, it's like if I have X and Y, if X is positive and Y is negative, that's the only reason they're together. We're going to talk more about ionic and covalent on Monday when we start talking about intermolecular forces and functional groups.
And DO is always positive.
What? Huh?
So was it A or C?
It's A.
Okay.
All right. Let's look at the back side of this, and then we're going to go back to that other handout and talk about isomers. And then that'll be it. We'll stop. So here, this just asks you to put the right dipole arrow in, right? What do we know about the dipole arrow? Which direction is it always going to point?
The more electronegative atom.
Yes, it's always going to point toward the more electronegative atom. So in a CF bond, which direction would it be pointing?
B.
Would it be pointed toward carbon or toward fluorine? Keep in
Fluorine.
mind, fluorine is all the way to the right of the periodic table. So it should point towards fluorine. Is that right?
Yeah.
What about HBr?
Point towards BR.
It's going to be pointing towards bromine. So it should be here. Carbon silicon bond. Keep in mind, electronegativity increases from left to right and from bottom to top. And carbon and silicon are in the same group on the periodic table, but silicon is underneath carbon.
So point towards carbon.
So it should be pointed towards carbon. And then what about the NO bond?
Oxygen.
Towards oxygen. Good. All right. Any questions about that? So on that first module, you're going to turn this handout in, and you're also going to turn in. I said I would take off the line structure one, but if you've already done it, you can turn it in. I'll just leave it.
Wait, I'm confused about number 7.
7 HBr.
Yeah.
Oh.
Like I know bromine is more electromagnetic than hydrogen. Yeah, okay.
I just picked the wrong.
Like, wait, that's wrong. Okay. Thank you for clearing that up.
Oh yeah. Thank you for seeing that, because you're the only person that says so. Everybody else is asleep. Well, not everybody. Let me go back to this other. Well, I got it.
Dr. Russell?
Yes.
I had a question on like the bonding hybridization informal charge sheet.
Okay, that's the one that I just took down.
If it was connected to the assignment one, then
Yeah,
probably, I think, yeah.
Make sure I open the right one. Okay, what's the question?
I don't think this is one of the ones like we did in class, but 1.68, like part like C and I mean D is kind of similar. I don't know if your screen changed or not. I don't really like see what's wrong with them.
So explain. Okay, great. Oh, good question. I gotta mirror my screen. Give me 1 second. That's a great question. All right. So if you look at C, right? Everything is fine except for this. What's the problem there? That's somebody asked me this way back. Not like we've been in class forever, but somebody asked me this question. What does that indicate that the sigma bond is 2? What that's telling me, if I see that, it's telling me that the H is what's bonded to the ring. And that's not possible. Hydrogen can only make one covalent bond.
Oh, okay.
Right, it can only make one bond. So the way it's written, that's a problem. That's why normally if you see the OH on the left side, you'll write it like this.
Mm.
And then if it's on the right side, you can just write it like that.
Okay.
Good question. I'm glad you saw that or got tripped up on that. That's a good question. All right, what's wrong with D? Do you see the negative charge right here?
Mm-hmm.
When will carbon have a negative charge? What am I missing? Right, it's a couple of things wrong. First of all, carbon has 4 bonds already. So it's got a full octet. So if I put a pair of electrons here to make it have a negative charge, it's going to give it 10 electrons and not 8. Are you following?
Yes.
Yeah. So if it's 4 bonds already, anytime carbon already has 4 bonds, it's not going to have a charge on it.
Okay.
So you exceed the octet rule. All right. Good question.
So is it because I notice a lot of times when it forms the like the ring shape, they'll have like double bonds and stuff like that, like inside of it.
Mm-hmm.
Does it have to have those double bonds? Because before, like you said, the O is the one that's supposed to be closer to the inside of the ring. I didn't know like if it was a problem because it was missing double bonds and stuff. And
No.
Why can't those be like CH2s or something?
No, all that's case by case.
Okay.
Yeah, every structure is different. So no, it doesn't have to have double bonds.
Okay.
Yeah, good question. All right, what's wrong with this one? The ring is fine, but look how the carbons are attached on the outside. Right, what is that? What is this? What's wrong on this side? If I attach a CH3 to the ring.
There's too many bonds.
There's too many bonds to carbon in it. So that's why, for this example, it should be written like this. Like a CH2 and then a CH3. Hold up. Right, so now we know what atom is actually bonded to that ring. It's the CH2, the carbon from the CH2. And then of course this is still the same. I don't have to rewrite that.
Mm-hmm. Okay, thank you.
All right. Any other questions? We can take some more questions. I think we're gonna wrap up a little early today. Any questions off either handout?
Can you go back down a little to 1.68, please?
1.62?
I mean, the one you just got finished working on.
Okay.
Thank you.
Right here, 168.
Yeah.
Which one did you want to look at? Or were you just writing it down?
Yeah, I'm still lost on C.
On C?
I'm kind of confused. On C.
Yeah, so let me zoom back in on that. Do you see how it's written?
Yeah.
So the way it's written is indicating that the hydrogen is what's connected to the ring. You see that right here?
Mm-hmm.
Well, hydrogen can't make more than one bond. Right there, it would look like it would be here, and that's the ring. And then oxygen will have, if you wrote it like that, that's what it really would look like. Where oxygen is negative, and then H is what's connected to the ring. But H can't make more than one sigma bond. So you have to write it like this, with the oxygen being the atom that's connected to the ring.
Oh, because you can only have one bond. Okay.
You can only make one bond to hydrogen.
Okay.
But the way it's written is showing it as if it has two bonds to hydrogen, one to the ring and one to oxygen.
Oh, okay, yeah. Okay, I get it. Thank you.
Right. Yeah. Let's do another one of these. I like these. What's wrong with this carbon?
Too many bonds.
Too many bonds to it. Is that right? This is what it would look like if I drew it out in Lewis form. Except I'm not drawing out the CH3s. But that carbon in the middle, if we count up, it's got one. Well, no, let me not do that because I'm not looking at the atoms. It's got 1, 2, 3, 4, 5 bonds. Right? That'll never happen. You always want to have 4 bonds to carbon. And if you don't have 4 bonds to carbon, anything less than that, you got to have a charge, either a plus charge or a negative charge. And it'll never have more than 4 bonds. Ever. Ever, ever, ever in life.
Okay, so would that be considered exceeding the octet rule or just a rule that it never have? Okay.
That's why it makes 4 bonds, because that's how it completes its octet. So if you go over that, then you're gonna have 10 electrons and not 8. So yes, it would. That's exactly right. It would be exceeding the octet rule. All right. Any other questions? I think we got some good work in dealing, but we touched a lot of topics, so that's why I was kind of scattered. But let me just kind of recap what we've done up to this point. Right. So we talked about, first thing we talked about was hybridization. Hybridization. Is that right? Do y'all remember that? So you can have sp3, sp2, and sp. And then the second thing we talked about was we talked about formal charge. Yeah. We talked about bonding and dipoles. And we talked about resonance. Spent the most time on that. What else? What else? Am I missing something? Because there's a lot that just these 2 topics right here had a lot of underlying topics that we talked about too. Let's see. I slipped in some functional groups, but we're going to talk. And Lewis structures and skeletal and line structures. All right, we talked about that. skeletal forms, condensed forms. And then Lewis forms. How to convert between the three, right? We can go from either one of those. We can go from Lewis to skeletal, from skeletal to Lewis, from Lewis to condensed, so on and so forth. What am I missing?
I think you covered everything.
Yeah. It doesn't look like a lot, but we talked about a lot of stuff. So, the exam.
I have one more question.
Go ahead.
It was like the first thing that we did on the first worksheet.
Mm-hmm.
When you said when like CH, when like different, like when they're in parentheses, which one does it belong to the left or to the right? I forgot.
Well, okay, so if it's on the end like this, can you see the screen? See how that's on the end?
Yeah.
Right, so there's nothing to the left of it. So it's got to be bonded to the carbon on the right, and the same thing here. That's to the left of it. Right, but when you have something like this, right, you see how the atom is in parentheses, that's going to be bonded to the atom to the left of it.
Okay. All right. Thank you.
Mm-hmm.
I just wanted to confirm, Dr. Russell, that the worksheets are due on Sunday, right?
Yeah. You can turn them in if you got them done and you're in Blackboard. When you upload your test, you can upload your homework.
Okay,
I would just do it all at the same time so that you don't forget. Normally, I think it says in the syllabus that it's due the day after the test, but just if you're done with it, just upload it.
Okay.
All right. Any other questions? Man, the time went by so fast. All right. So you'll get an announcement when the exam has been deployed. But for now, take a deep breath. If you got other classes, focus on that, because you'll have all the way until Sunday to finish that exam. All right. Are we good? All like church, all hearts and minds clear?
Yes.
Ready for the benediction?
Yes.
All right. I'll see y'all on Monday. I'm gonna send you some videos over the weekend for Monday, dealing with functional groups. I'm gonna warn you up front. These are like some of the first videos that I made when I started doing flipped classroom. So they're a little long. Some of them have a little music, some don't, but the ideas and concepts are what's important. So it might be a little boring. Take a break in between, whatever you need to do to get through them. But I think it's like 4 videos.
What's long?
8 minutes.
That's not bad.
Okay, well, good. I'm glad you said.
I had teachers send us like 20-minute videos, and I'm like,
no,
I got other classes.
That's too long, especially if you're just sitting in front of a screen. That's too long.
Yes, Lord.
Yeah, my attention span is short sometimes.
Yeah, the internet has done that to us, right? Because with TikTok, what you got, a minute on TikTok to make your point, 30 seconds to make your point?
Not even a minute.
Yeah, I'm telling you.
But when would a video that you did today be posted on YouTube?
Say that again.
When would a video?
I'm going to post this as soon